Good morning everyone. I am Dr. Murugalakshmi, Associate Professor and Head, PG and Research Department of Chemistry, the Standard Fireworks, Rajaratnam College for Women, Sivagasi. And today we are going to see the topic neighboring group participation. So first let us see the definition for the neighboring group participation. It is a phenomena in organic chemistry where a functional group within the same molecule, that is you can take only one molecule and in that molecule adjacent to the reaction center but not conjugated with it, interacts with the reaction center. So that is the speciality of this neighboring group participation. So simply we can say intramolecular interaction which facilitates the departure of the leaving group and increases the reaction rate in multiples, that's called anchimeric assistance. And this can also lead to unexpected stereochemical outcomes such as retention of configuration by forming a cyclic intermediate before the final nucleophilic attacks. And who else can act as a neighboring groups? We can say the examples as heteroatoms with lone pairs. Heteroatoms in the sense sulfur, oxygen, nitrogen, like that. And we can also say examples halogens, chloride, bromide, iodide, alcohols like OH groups, amines, NH2. That is, they are having lone pair of electrons on their head. That is, if when you take OH on the oxygen head, you are having two lone pairs, and in amines you are having a lone pair of atom. And the second thing is pi bonds. The pi bonds may be present in the alkene rings or it may be present in the benzene nucleus. So what are the key aspects that we can discuss now? First one is rate acceleration. This is a very important thing. Normally we can't expect such a rate acceleration when we use a catalyst, but because of the presence of the involvement of the neighboring group, which leads to the faster reaction rate compared to the normal reaction without this interaction. And the next one is, next key aspect is, it can also cause abnormal stereochemistry. Most notably, the retention of configuration at the reaction center. Normally we can expect the inversion of configuration, but here the retention of configuration at the reaction center occurs, which differs from the inversion seen in a standard SN2 reaction. And the another thing is, the neighboring group attacks the electrophilic carbon, forming a stable 3-membered or 5-membered cyclic transition state before the incoming nucleophile attacks. And this cyclic intermediate, it's very planar, and it gives the way for the retention of configuration in the stereochemistry of the product. And it involves the two-step mechanism. The process involves two successive consecutive SN2 reactions. Normally SN2 means substitution nucleophilic bimolecular. It is a single step process, and here two successive SN2 processes are taking place. The first by the neighboring group and the second by the external nucleophile. So what are the suitable neighboring groups? Functional groups, again I am repeating the same, heteroatoms, atoms like nitrogen, oxygen, halogens with lone pair of electrons, and the electrons in a pi bond of the benzene ring or an alkane. And the important aspect is geometrical requirements, it's very important. The neighboring group must be positioned correctly. Often it may be in the beta position or in the epsilon position. That is, functional group present the carbon which is having the functional group or which is having the leaving group, and to that carbon, that's called alpha carbon, and to the next carbon, that's called beta carbon, or it may take place in the epsilon position to facilitate the formation of a stable ring. So two SN2 substitutions we can see in the scheme. First step, the neighboring group which is present in the beta position, which is named as Y dot, and it is anchoring on the carbon center, and it is kicking out the leaving group L out of that molecule, and this is the first step, which is a rate determining step, and just like that of the SN2, and it is forming an intermediate cyclic transition state Y plus. If it is a carbon, we can say it as carbonium ion, and if it is a halogen, we can call it as a bromonium ion. And in the second step, the nucleophile which is going to enter, it will come into act, and it is a fast step, and we are getting the product. So first step is the attack of the internal nucleophile. This is a neighboring group participation step. Second step, substitution of an external nucleophile which is leading to the product formation. So unexpected behavior in the stereochemistry, retention of configuration. The second one is it is following the first order kinetics. We can see the very simple example, the participation of the double bond as a neighboring group. Properly placed pi electrons of a carbon-carbon double bond in a substrate can function as a neighboring group. Here the stereochemistry is again a retention which is extremely fast, which is following very fast reaction kinetics. The rate is 10 power 11 times faster than that of the saturated substrate. We can see that example in the table, that is in the box. We can see tosylate group, norbornyl tosylate. See here the double bond which is present is acting as a neighboring group, and it is anchoring on the carbon which is having a leaving group OTS, that is tosylate group. And when acetic acid come into play, the relative rate will be enhanced to 10 power 11 times. The same reaction when it is carried out in the saturated compound, that is nearer to that reaction, here the relative rate is only 1. So the double bond, the mechanism is given, the double bond is acting as a neighboring group. It anchors its position to the carbon which is attached to OTS. So it is driving that OTS in a faster way and makes the reaction to be very faster. The ability of the carbon-carbon double bond to serve as a neighboring group, it depends strongly on the electron density. See, if we are having trifluoromethyl group, that is a highly electron withdrawing group. If they are present in the substrate, the solvolysis rate is lowered severely. Similarly, we can also take the example of benzene ring pi bonds as a neighboring groups. Here when you are having two reactions, first reaction it is ethyl tosylate, and in the second one we are having phenyl group as an assistance. So here when you are having the trifluoroacetic acid as a attacking reagent, the relative rate is 1. But you see the nearer reaction which is having a substituent phenyl ring, and that phenyl ring it is having pi bonds in its structure, and that pi bond is participating as a neighboring group, and it strives the OTS group to leave the molecule easily. So the relative rate is increased to 3000 times faster than the first one. With no heteroatom containing a lone pair, it must be the presence of the benzene ring only. The first reaction, it's a standard SN2 reaction, while the second one results from two SN2 reactions. We can see in the scheme, the first step, the phenonium ion will be formed as an intermediate, and that will be giving rise to the product, the next step. Similarly, heteroatoms, another example is a heteroatom. See the reaction here, if you see that reaction again, acetic acid rate of solvolysis in tosylate molecule, here the acetylation process is 670 times faster than that of the reaction B. The reaction A proceeding 670 times faster due to the involvement of the tosylate group trans to that of the leaving group. When you see these two structures in reaction A, the OTS is present trans to that of the leaving group, whereas in the reaction B it is in the cis arrangement. Then next, when you take the sulfur case, here also the neighboring group is sulfur, the relative rate is 600 times faster than that of the first reaction. When you take normally CH3, CH2, CH2Cl, propyl chloride, you will get a propyl alcohol as a product. But when you are having this heteroatom sulfur, it enhances the reaction rate. The lone pair of electron present on the sulfur, it kicks the carbon which is bearing the leaving group chlorine and motivates the reaction. So the rate is 600 times faster. The sulfur can act as an excellent internal nucleophile and promote an intramolecular reaction. So the top reaction is a straightforward SN2 reaction. The bottom reaction, it is much faster because of the neighboring group sulfur. This creates a cyclic sulfonium ion. The mechanism is given in the scheme, so which involves a double SN2 process. Thank you.